Hello and welcome to another video. In this video we're going to be working on magic squares in a grid. And in this one you have a 3x3 square, which is a 3x3 grid filled with distinct numbers, such that each row, column, and both diagonals have the same sum. Given a grid, how many 3x3 magic squares are there? Note while magic square can contain numbers 1 through 9, grid may contain numbers 1 through 15, or 0 to 15 I guess. Yeah. So in this first example, this is a magic grid because all of these, everything adds up to 15. And this one does not. Most of these add up to 15. Like this is 15, 15, 15, but something like this, for example, doesn't. And this isn't either. So there's only one. And the second one, there are no 3x3 grids. So how would you do this? And the important thing to think about is constraints. So let's say we just have some big grid like this. So first of all, how long does it take us to go through a 3x3 grid and figure out these things? Like we'd have to total the rows, total the columns, and all that stuff. And so in order to do all that stuff, you're basically going to go through this grid like 1 or 2 times or something. But basically, if this is a 3x3 grid, it will take us roughly 3x3 amount of time. And then let's just say we have some big matrix. How many 3x3 grids are there? So there's pretty much, if we have like rows and columns, there's something like this. Rows minus 2, columns minus 2, 3x3 grids. Because if you think about it, let's just think of like the top left start of a 3x3 grid. Any square in here can be that except for the bottom 2 rows and the bottom 2 columns. But anything else can be a valid start, right? Like this can be 3x3, this can be 3x3, this can be 3x3, and so on. Like if you just say what's the top left point, so it's roughly m by n. Yeah, rows and columns, and then to go through one grid is roughly 10. And so because these rows and columns are kind of small, they're 10 and 10. Our time complexity would be like 10, 10, 10, something like that, roughly. You might have to go through the grid a few times. Maybe it's like 10, 10, 10, you know, even if you go through the grid another 10, it's still fine. And so we can actually just basically brute force this, where we can say like, okay, let's just go through every single starting point of a 3x3 grid and just check for all these things. So we can say like, okay, let's start here. Let's go through the 9 cells that would make it a 3x3 grid. And then what do we have to check for? So we have to check for every value between 1 and 9. So that's pretty easy. Unique values, you can use a set. Row totals, all same, pretty easy, there's only 3 rows. Column totals, all same. Diagonal totals, all same. And so to check these 2 things, you can go through the grid once. To get the row totals, depending on how you write it, like maybe you'll go through the grid again here, go through the grid again here, go through the grid again here. So you go through it like 3 or 4 times or whatever, it doesn't really matter. So you can basically do that and that will pass. And there's a couple like optimizations you can make, but it's honestly not the biggest of deal. Like even if you didn't come up with them, it'll still be fine. And some optimizations are, so if you think about it, all of these values, so if you take 1 through 9 and add them together, so we can do that really quick, right? So this is 11, 15, 15, 15. So a 1 through 9 grid adds up to 45. And so the row total, if there's 3 rows of equal length or of equal value, has to be 45. So every row has to be 15. So every row has to add to 15. And because the row and column and diagonal are the same for the rest of them, right? So every column has to add to 15. Every diagonal has to add to 15. And so you can do this to like break early if you want to. And another thing you can think of is like, let's just think of all the ways we can get to 15. So let's say we have 1 plus 9. What would that last number be? So that would be a 5. That's one way. Then we have 2. Let's say we have 2 plus 9 again. and this would be 4, right? Yeah. And then we can also do 3 plus 9. And we can't have the same value here, so this wouldn't actually be possible. So 3 plus 9 is not possible. So 3 would have to add, let's just add like some other number. Well, let's keep the middle number 9. So let's see what else we can do 3. Can we do 4? So 4 plus 9 would be 13, and then we could do 2, but we already have that. So and then I think that's it, right? Yeah, so basically 9, the only way 9 can be like this middle value is these two combinations. Okay, well, what about 8? So 8, let's start with 1. So this would be 9, and then we would get 6, and then 2, 5, and then 3, 4. And anything else would just be the reverse. So that's how many ways you can get 8. Then what if we have 7 in the middle? So this would be 4, 7, 3. 3, 7, 4 is repeated. And then 2, 7, 5. And 1, 7, 6. So that's the only way to have 7. And then what about having 6 in the middle? So that would be 1 plus 6 plus 8. And then we could have 2 plus 6 plus 7. 3 plus 6 plus 6, so that wouldn't work. Okay, 4 plus 6 plus 5. And then anything else would be repeating, so that's 6. And then to have 5 in the middle, so I guess we can keep these like separate just to make it easier. So maybe we can do like this, this. But honestly, all of this is extra, but anyway. So yeah, so if you want 5 in the middle, so it'd be like 1 plus 5 plus 9. 2 plus 5 plus 8. 3 plus 5 plus 7. 4 plus 5 plus 6. And I think that's it. Yeah, because you can't do, yeah, so I think this is it. Okay. And then for 6 in the middle, we already did that. 7. So if we need 4 in the middle, so for 4 in the middle, it'll be 1 plus 4 plus 10, which we can't do. So 2 plus 4 plus 9. And then it would be 3 plus 4 plus 8. We can't do 4 plus 4, so 5 plus 4 plus 6, and everything else will be repeating. So you can kind of see a pattern here. I can keep doing this, but basically the 5 can have 4 values. And like I said, this is not really super, like, you don't really have to see this. This is kind of like extra. You don't really need this for this problem, just to show you. So the 5 has 4 values. Like the 5 can make a 15 in this way. Every even number can do it in 3 ways. So 6, 4, 8, 2 can do it in 3 ways. And every odd number can do it in, I think there should be 3. Yeah, so it's like 1, 2, or it might just be 2. Maybe I screwed this up. Let's see. So this is actually not, yeah, this is screwed up. So this is 7, so this is incorrect. So it's like 7, 1, and this should be 7, which doesn't work. And then 2, 7, and 6, and 3, 7, and 5. Okay, there we go. So you can keep doing this for every number. So basically, odd numbers have 2 ways, even numbers have 3 ways, and a 5 has 4 ways. So if you look at this thing, like let's say for this grid, because a 5 can make 15 in 4 ways, 5 has to be in the middle because the middle number will make 15 in 4 ways. It'll be 1, 2, 3, 4. And then these corners are going to make 2 different things, right? So it'll be like 1, 2. And then these will make 3. So because these make 3, these have to be these evens. And then these have to be the odds. So it always has to be some combination of this. And so you can check for all these things as well. Like you can make sure like the diagonals are these numbers. Then these corners are like these numbers in the middle is a 5. But all of that is just like extra stuff. And so Yeah, so basically you can check for these things. It might make your thing a little faster, especially just checking if the middle is a 5 or if any total is 15. But you can keep getting like more and more things. There also has to be like some specific sequence. Like if you look at all these things and you just write out a bunch of different squares, there's only so many squares you can have, and then you can check for all that. So you can make it like a little bit faster, but it's not going to be like big O faster. Okay, so let's just take a look at the code. So essentially all we have to do is, like I said, if we have this big thing, we can just check. We can just say like every dot is the start of a 3x3 square, and then we can just check, is that a valid square? And so that's basically what we're doing. Everything except for the last 2 rows and columns, let's just check if it's a valid square. And so the middle has to be a 5, so if it's not a 5, we can return false. Our sum that we're summing to is 15, and all our values have to be unique. So we can go through our rows, and we can get all the values. We can go through the rows and columns and get all the values. And then if the value is out of bounds, or if we've seen it before, so instead of using visited set, just use an array, then we return false. And then we calculate the row sum for the row. And then if the row sum is not 15, it's false. Then we do the same thing for the column sum. So we calculate the column sum for every column, and it has to be 15. And then we get the 2 diagonals. So you can hard code or whatever. A nice trick you can use for diagonals if you have some big thing to recognize, and this does actually come up, is if you want the left diagonal, the row will equal the column. So you could check that. For 3x3, it doesn't really matter, but for big diagonals, you can easily check if that's part of like the main diagonal of a square or your grid. Because here you can see it's like 3, 3, 4, 4, 5, 5, and so on. And also, if you go down some other diagonal, the row and the column difference should be the same. So for example, here the row is 0 and the column is 1, so the difference is 1. Here the row is 1, the column is 2, and so on. So here the difference, like if you just do like column minus row, that's always 1. Then here it's always some other number, and so on. So that's how you could do the left diagonal. And then the right diagonal is pretty similar, except the main diagonal, the row and the column are going to add up to some number, and it will always be that number. So row plus column will always add up to some number. So in this case, it's 9. So like we have 9, 0, 8, 1, 7, 2, 6, 3. Same thing for this. This will always add up to some number. This diagonal here, I think I misdrew it. It's like 8, so this will be 8 all the time, and so on. So that's how you check like what diagonal I'm in. Am I in the main diagonal? It's not super relevant for a 3x3, but it's good to know for like bigger stuff. So hopefully that's helpful. Yeah, so we just check for all these things. We basically just brute force this whole guy. And you don't need these optimizations. Like you can have them, but if we just take out every single optimization, it will still work. Like we can just say like, let's just calculate the sum of the first row, and then everything else has to equal that. So we can instead of like knowing that our sum was 15, we can just say, let's just get the sum of the first row and get it that way. And you don't need to know the middle is 5 or all that. It's just more like unnecessary, but you can come up with them. So yeah. So for this, so basically we can say that this is like n by m, and then every single grid will be constant time because it's just a 9 grid, and then space is constant because even though we did make some diagonals and rows and things, they're all only, there's only 3 rows and 3 columns, so it's all constant. So hopefully that was helpful. If it was, please like the video and subscribe to the channel, and I'll see you in the next one. Thanks for watching.